Hi everyone, I'm Jin-Peng Liu from University of Maryland. Today I'm glad to talk about quantum accelerated multi-level Monte Carlo methods for stochastic differential equations in mathematical finance. It's a joint work with Dong, Noah, Ashley, Changpeng, and Jiasu. Here are some openings. We are interested in general stochastic differential equations which can be used to characterize dynamics of financial market. For financial problems, we usually perform Monte Carlo methods to compute expectation values arising in option and derivative pricing. But when each sample is costly, overall the computational cost can be epsilon -2 minus alpha, for which alpha is a positive number, which can be significantly larger than the sampling capacity epsilon -2. Fortunately, in classical community, we are able to develop advanced Monte Carlo methods or fast sampling methods to remove such an additional factor to achieve epsilon -2. In a quantum analog, our contribution is to establish the first general quantum acceleration for payoff models of general stochastic differential equations with the cost epsilon -1. Then we perform our quantum algorithms to different kinds of financial models corresponding with various payoffs. In our talk, I would like to introduce two kinds of methods. The first one is the quantum accelerated multi-level Monte Carlo methods, and the second one is the quantum accelerated Monte Carlo methods with binomial sampling. So here is a problem model. We consider a general stochastic differential equations with general coefficients as equation 1. Then for the payoff model, we are able to sample from an initial distribution pi0 to produce an initial state pi at 0. Then, given the evolution time t, we aim to compute expectation of payoff p of st within a diff error epsilon. Here, p of s as a function of s is the payoff widely investigated in mathematical finance. So here are some particular SDEs we are interested in, such as for the Black-Scholes model, we are concerned with such a particular geometric Brownian motion. For the local volatility model, we care about a modified version of the geometric Brownian motion, which will replace the time and independent coefficient sigma as a function of st and t. Finally, we care about grids, which means sensitivity of price of derivatives. So for this problem, we care about a couple of general stochastic differential equations. Then we care about some payoff models arising option pricing and hedging problems, such as the well-known European option, the Asian option, and digital option, aka cash or nothing option. In the most general case, we are interested in piecewise Lipschitz continuous payoff option, which can be used to approximate a large class of discontinuous payoff options. So for this problem, what's the computational cost in the classical Monte Carlo methods? Here we consider an example of first-order scheme. Suppose that we use such a scheme to produce a numerical solution Sn hat, which is epsilon close to the ideal stochastic solution St. Here we denote n is equal to capital T over h with the step size h. Since it's a string of strong order 1, we have the expected error or the bias decrease linearly with the n That means in order to achieve the bias smaller than epsilon, which has the scaling n is n as epsilon minus 1. That means in each sample, we are required to simulate Sn hats with the cost n, which means with the cost epsilon minus 1. Then in the outer loop, we perform Monte Carlo methods to estimate the expectations. So we should generate capital N samples with capital N scaling as epsilon minus 2. So the overall computational cost is linear as capital N times N, which is epsilon minus 3. In general, using a string of shown order R, which means the error scale as h to the r, we have the overall computational cost scaling as epsilon minus 2 minus 1 over r. So that means the cost can be larger than the sampling complexity, which is not ideal. In the classical community, multi-level Monte Carlo methods are developed to solve this problem. Multi-level Monte Carlo was proposed by Michael Giles in 2008. Here is the basic idea. If we aim to estimate the expectation of a random variable p, then we develop a sequence of estimators p0 to p capital L with increasing accuracy. Then we consider a telescoping sum, the sum of expectation of PL minus 1 to estimate expectation of P. Then we denote the cost, variance, and sampling number of each term are CL, VL, and capital L. Here, remark that the CL increase with L, VL decrease with L, and the sampling number capital NL are different from each other. Then, if we aim for multi-level Monte Carlo methods has a better performance than the standard Monte Carlo method for the estimated P capital L, it should satisfy two conditions. The first one is the overall variance, the sum of NL minus 1 times VL should be close to the variance of a single estimator. The second one is the overall cost. The sum of NL times CL should be much smaller than the cost of a single estimator. So we should satisfy these two conditions. This is exactly an optimization problem. Given a fixed variance, we aim to minimize the overall cost. One can show the optimum is epsilon minus 2 times additional factors depending on VL and CL, given by the optimal choice of sampling number. Furthermore, to cancel out the additional factor, we require the increase of CL is no faster than the decrease of VL. We observe that because CL is increasing and VL is decreasing, so if the VL can cancel out CL, then this additional term can be equal to a constant. The above is a very general description for the estimators to the variance to random variables. Then we perform this framework to our particular payoff model. Here we set P as the payoff with the ideal solution ST, and estimators PL is equal to the payoff with the numerical solution SNL hat. So each PL is produced by a certain string with discretization NL. Here we set a binary discretization, which means each time we simulate the numerical solution, taking the cost 2 to the L, and the variance should reduce as 2 to the minus beta L. Here, if we have the condition beta larger than or equal to 1, which can be ensured by a string of Shao order R larger than 1 for general piecewise payoff, or R larger than or equal to 2 for globally Lipschitz payoff. Then the conclusion is the classical multi-level Monte Carlo method can achieve the overall cost epsilon minus 2, which is equal to the sampling complexity. Now we are going to talk about the quantum acceleration. So as we know, the well-known result proposed by Montanaro in 2015 is the quantum speedup of Monte Carlo. The description is given an algorithm A, which can be either classical or quantum algorithm, which has access to visit the value of a random variable. Then given a fixed variance, there exists a quantum algorithm that estimates the expectation of V up to a dp error epsilon with probability in certain cost epsilon minus 1, which is a quadratic speedup compared to a classical case. For Shaw's models with closed form solutions, this strategy has been applied to estimate the price of options with a quadratic speedup in low precision. However, it cannot be generalized to simulate stochastic differential equations without the closed form solutions. This is because if we are not access to the final solutions, we require to run down numerical schemes, so we must suffer from some cost from the numerical simulations. So in that case, we should consider the multi-level Monte Carlo methods in order to reduce such an additional cost. So in our paper, our contribution is to generalize the multi-level Monte Carlo method to the quantum case, and each time we can reduce the sampling number of each turn in the test grouping sum from epsilon minus 2 to the epsilon minus 1. So here is the conclusion of our theorem. In our theorem 2 of our paper, we consider a very general setting of multi-level Monte Carlo method. As above, we denote P as a general random variable and let PL be estimators. Then we use alpha, beta, and gamma to represent the decreasing rate of expectation, the decreasing rate of variance, and the increasing rate of cost. Then if we have the condition half of beta larger than or equal to gamma, then there is a quantum algorithm that can estimate the expectation of P up to a diff error epsilon with certain probability in a cost epsilon minus 1. So here we are able to achieve a quadratic speedup in the overall computational cost. But the new optimum we developed requires a twice faster variance reduction rate beta. That means we require PL approximates P with higher accuracy. So here we can use this general result to our payoff models. That means, again, we set P as the payoff with ideal solution, and PL is the payoff with numerical solutions. Then compare the decreasing rate of variance and increasing rate of cost. Here we require half of beta is larger than or equal to 1. So our theorem 3 sets the quantum accelerating multi-level Monte Carlo with a string of Shao order R larger than 2 for piecewise Lipschitz payoff, or R larger than or equal to 1 for globally Lipschitz payoff, that can estimate the expectation of P up to a diff error with certain probability in a cost epsilon minus 1. Compared to the classical condition, we can find that we require a string of Shao order twice larger than the cluster case. That means we both require higher smoothness assumptions of the SDEs and require higher order numerical strings, which can be guaranteed by a stochastic version of longitudinal strings. So that is the first result we aim to talk about in this talk. Secondly, I would like to move forward to talk about quantum accelerated Monte Carlo methods with binomial sampling for binomial option pricing models. So here we know the price of stock can be governed by some stochastic differential equations. In a board, we consider to use some numerical scheme to discretize the time. Then alternatively, we can consider a different kinds of Markov chain in discrete time to approximate the stochastic differential equations. Here we consider a very simple Markov chain as equation 11. The price of a stock either goes up or goes down in discrete time. So sk plus 1 is equal to sk multiplying yk plus 1. And here yk are class of 2 points distribution. Rk is equal to u with probability p, or yk is equal to d with probability 1 minus p. In that case, we can find sk indeed forms a binomial tree or a binomial random walk following the binomial distribution B and P. In order to ensure this approximation matches the realistic financial case, we should choose proper value of the probability P, the up price and down price U and D to ensure the conditional expectation and conditional variance of the binomial tree are the same as the Shaw's model. So similar as above, we consider general payoff models. We aim to compute the expectation of payoff models with the financial price ST within a certain additivity error epsilon. Here we use P is a piecewise constant payoff option. Then the crucial lemma we use is the recent result, the so-called sublinear binomial pricing. Given the value n and p, then the sampling from a binomial distribution B and P only requires both the expected samples and expected time as log n complexity. So that means in each sample, sublinear binomial sampling can provide a way to simulate P of ST with ignorable cost epsilon log 1 of epsilon. That means in this cost, each cost can be neglected. So the standard Monte Carlo method can work and the sampling complexity is equal to the overall computational cost. So this can be regarded as a reduced case of multi-level Monte Carlo approach. So in our paper, we did both classical and quantum algorithms with standard Monte Carlo methods and with the sublinear binomial sampling to estimate the expectation of price up to a additivity error with certain probability in the cost, both epsilon minus 2 and epsilon minus 1. In our paper, we use this table to summarize the time complexities of the classical and quantum algorithms for financial models. Then we can see the first 4 kinds of classical algorithms aim to achieve the complexity epsilon minus 2 or larger. Then the last 4 quantum algorithms aim for achieving the complexity epsilon minus 1 or larger. So quantum algorithms can achieve a quadratic speedup compared to the classical analog. Then if we consider the Shaw's model, which we are able to sample from the final solutions, we it's easy to perform the standard Monte Carlo method with direct sampling to achieve the optimal epsilon. But for general payoff models or for binomial option pricing model, we should perform either a multi-level Monte Carlo method with string option order larger than some constant, or the standard Monte Carlo with binomial sampling methods in order to achieve epsilon 2 to the classical case or epsilon 1 for the quantum case. So the results in red are provided in our paper. That means we establish the general quantum accelerations for the general payoff models of general SDEs and for the binomial option pricing model. So in summary, we provide a projective quantum speedup of multi-level Monte Carlo methods in a very general settings. And then we demonstrate a variety of applications arising in mathematical finance, such as option pricing, local volatility model, and grids. Alternatively, we also provide both classical and quantum algorithms based on sublinear sampling for binomial option pricing model. We have some open questions. First of all, can we generalize the model to the more complicated path-dependent payoffs? Secondly, can we provide other characteristics beyond the expectations for the stochastic process, such as the variance? Finally, can we find potential exponential quantum speedup for problems arising in finance? So that's all. Thank you for your attention.